All righty. All right, so the reason that we kind of stop right here and do this little unit is because net ionic equations are used a lot with acid-base reactions, specifically with titrations, which is where we're moving on in our other set of notes on Wednesday. So on a net ionic equation, there are several steps that we're going to take to get to the actual net ionic equation. In a net ionic equation, it's an equation that shows only those species that actually are participating in the reaction. We cancel out the spectator species. That's what we did on the journal. And we can do that if they're on both the reactant and the product side in the chemical reaction. And that's because they do not actually participate in the reaction. They're just there in the water as ions. So net ionic equations are commonly used in neutralization reactions, which we've done before, and that's where we do our acid, a strong acid and a strong base, double replacement reaction, and redox reactions, which we may or may not get to. So on these, we're interested in looking at the strong electrolytes. So that would be strong acids and strong base and anything that's soluble in water, because those are the ones that will exist as ions in a water solution. So on your first step, you're just going to write the molecular equation, which is what we've been doing, and balancing it. So that's just the equation without anything that's represented as ions. They're just represented as an element or the compounds. One thing that you do have to do that we didn't do a whole lot of, although we did with double replacement, you need to put what state they're in, whether it's aqueous, solid, liquid, or possibly gas. Then you're going to have to do your total net ionic equation. And what you saw on the board in the journal, that was a total net ionic equation. So anything that is AQ should be ionized. I'm not trying to cross those out. Anything that is AQ should be ionized and broken up into its ions. There are some rules below that'll help you, and then also you'll be dependent upon your solubility rules. And that's the other thing that you picked up on Friday, just a real simple version of solubility rules. During double replacement reaction, we also use solubility rules, but this one is just kind of a very simplified version. Definitely does not cover all of the solubility rules, but we're kind of just looking at the big picture. All right, so things that will break up into ions are all of your strong acids. So I've told you to memorize those, and once again, you'll need that whenever we're in this little portion. Our strong base, so group 1 and 2 hydroxide, except for beryllium and magnesium. Soluble salts, so there are some that are always going to ionize. Anything that has ammonium in it, NH4. Anything that has nitrate in it, those always ionize. And also salts of the alkaline metal, so that's your group 1 metals. So those are kind of your easiest ones to recognize without kind of looking at the solubility rules. The ones that do not break into ions that you're just going to leave as compounds are weak acids, weak bases, insoluble salts. So once again, that comes from your solubility rules. And then non-electrolyte or weak electrolyte. So those are water, gases, pure elements, hydrocarbons, and alcohols, although we will not do many of those, or probably won't do any of those. So we'll be doing water a lot. So water will be a liquid, and liquids do not ionize. And then you may see some kind of common gas. Those don't ionize because, of course, they escape from the solution before they would happen. And pure elements are in the states that they exist on the periodic table, and that would include your diatomics. To get from your total ionic equation to your net ionic equation, you have to take out your spectator ions. And we said these are the ones that you can find on both sides of the equation. and you want to remove the spectator ions from the actual equation. And what remains is the net ionic equation. The final net ionic equation must be balanced in regard to both atoms, which we've been doing all along, and charge. So what I mean by that, if your reactants overall have a 2+, then your products have to have a 2+. If your reactants, when you look at everything, have a no charge or it's neutral, then your products have to be neutral. If all the ions are spectator ions, then that means you have nothing left to actually react and you end up with an NR. So we've also talked about that before. That would come from a double replacement reaction where your product would be 2 AQs. And that's going to equal an NR. So sometimes if you can recognize that at the beginning, you don't have to wait till you get all the way down to canceling spectator ions. You can just see, all right, I have a products and they're both AQ, so that's an NR, and then you don't have to continue with all of your work on there. All right. If you look at your little solubility rules I gave y'all yesterday, like I said, by no means is this a complete set of solubility rules. It's kind of a very basic set. And on quizzes, on tests, I'm going to try to keep it where you can get what you need off of this very basic. You may come across in your practice some that you can't really find on here. You'd have to pull out your old solubility rules. But for the quiz or the test, I'm going to try to keep it off of these. So some of these we've already mentioned. So something is soluble means it will, if you remember, soluble means it's going to be AQ, aqueous. It will dissolve in water. If it's unsoluble, then it ends up being an S for solid. So these are the rules for solubility, things that will be soluble or will ionize. As we said earlier, group 1 metals, anything attached to ammonium ion, that compound's going to be soluble. Nitrates, acetates, and chlorates, those are all soluble. All halogen, so that's group 17, all halogen compounds other than fluoride are soluble except silver, mercury, and lead. So like on our warm-up today, we had lead chloride. So the reason it wasn't soluble is because that was an exception. So that made it a solid when it was produced. All sulfates are soluble except, so these are my exceptions, barium sulfate, strontium sulfate, calcium sulfate, lead, silver, and mercury 1 sulfate. All of those would be solids. If you can't find your compound on this first 1 through 4, if you don't find it in any of those rules, then it is generally insoluble and you would put it as an S for solid. And our main exception over something that would be an AQ or an S is water, because we'll have that a lot because acid-base reactions produce water and a salt, and the water is going to be a liquid. All right, so let's just kind of look at some of the practice because that's the only way you can start seeing how they work. Or not the practice, the ones attached to the notes. All right, so we just have to start off by predicting the products, which we've done before. So I have magnesium hydroxide. Oops. And at this point, it's a solid. And it's mixed with some hydrochloric acid that's in a water solution, so it's AQ. So this is an acid and a base reaction, and it's a neutralization reaction. We've studied those before, where the hydroxide from the base and the hydrogen from the water come together to produce H2O, which is my liquid. And then what's left comes together to form a salt, in this case, magnesium chloride. So what I need to do is I need to decide what magnesium chloride would be. Would it be a solid? Is it going to be an AQ? So I need to look at my solubility rules. And chloride is an halogen, so it can fall under number 3. All halogens other than fluoride with metals are soluble except for those of silver, mercury, and lead. That's not an exception, so this is also going to be AQ. Sorry, I ran out of space. It should really be behind it. So this is a good reaction. When we did double replacement reactions, we said we needed to have at least one solid, or we could have water as a liquid. That told us it was a good reaction, or we could produce a gas. So in this case, we have water, so it is a good reaction. So the next thing we would need to do would be balance it. So I noticed that I have 2 chlorines, so I'm going to put a 2 in front of my HCl. And then when I did that, that gave me 4 hydrogens. So I need to put a 2 in front of my water. Some of them may be balanced when you predict the correct products, or they should be real simple to balance. There's none on here that are very hard to balance. So if you get to one of those, then double check that you've written it correctly. All right, so now we need to go through and we need to write anything that is AQ as ions, anything that's AQ as ions. So magnesium hydroxide is not. So it's going to stay together as a solid. Magnesium hydroxide is not a strong base, it's a weak base, so it does not ionize. But the hydrochloric acid is a strong acid, so it's going to ionize into 2H plus 2Cl minus. And the reason there's 2 of each of those ions is because the coefficient of 2. My water stays together as a liquid. We said that's not something that ionizes. And then we're going to end up with our next one, the magnesium chloride. We said that was an AQ, so I'm just going to put it down here, Mg2 plus AQ plus 2 of my chlorides, AQ. And once again, we had a subscript of 2. That's why I had 2 chlorides. So that is my total net ionic equation. So the next thing that we need to do is we need to get rid of our spectator ions. So what's going to be our spectator ion here?
Chloride.
Yeah, the only thing we got is the chloride. That's the only thing that's available on each side of the reaction. So now I just put it back together. MgOH2 as a solid plus 2H plus AQ gives me 2H2O liquid, and again, let me get rid of that. My Mg2 plus AQ. If we've done it correctly, we should have the same number of atoms of each element on each side, which we do. And we also should have the same charge. So on my reactant side, I have 2 times a +1 for a total of +2. And then on my product side, because of my magnesium, I also have a +2. So that would be your final net ionic equation written like that. Does anybody have any questions on that particular one? So use your ion sheet to get your charges as you start making them ionize. Between that and your solubility rules, those are going to kind of be the big things that you're going to have to be using. All right. We can look at another one, number 2. I have silver nitrate and potassium dichromate. So I'm going to say AgNO3, and that is AQ. No, I'm going to write too big, so let me start back over here. AQ plus potassium 7AQ. Now this is not an acid and base, this is two compounds, so that's a double replacement. So my silver and my potassium, my two cations, are going to switch places, and I'm going to end up with potassium nitrate. Potassium is a group 1 metal, so they're always AQ, and nitrates are always AQ too. So either way I look at it, I get an AQ here plus silver chromate. And if I look at my solubility rules, and you go through all of them, nothing said about dichromate. That CR2O7, it's not mentioned in those 4 solubility rules. Silver is mentioned a couple times, but it's mentioned as an exception. So that means I'm going to go with the very last one that says, if it doesn't come up in these rules, then we're going to assume that it is insoluble and it'll be a solid. So that is a good reaction. I have one AQ and I have one S. I think I need to balance a little bit because I notice I have 2 silver. So I'm going to put a 2 in front of my silver nitrate, which makes me need to put a 2 in front of my potassium nitrate. And then I think I'm nice and balanced. So now I'm going to start ionizing everything. So I just start over here. I have 2 Ag plus. I'm not going to put AQ on these just to save a little bit of room. But when you wrote them on a quiz or on a test, you would need to be putting AQ after every ion. NO. Then there should be 2 NO3 minus 1. And then I move on to this compound, 2K plus CR2O7 minus 2. So that's everything in my reactants. And now I'm going to move on to my products. My potassium nitrate, I have 2 potassium plus 1. And I have 2 nitrates minus 1. And then this last thing, I'm going to erase a little bit here, is a solid. So it's going to stay as it is. Ag2O7. Ag2CR2O7. All right, so on this one, I have a few more. I have a couple of things that are spectator ions. So what are my spectator ions in this one? Nitrate and potassium. And since potassium is always soluble, and so is a nitrate, those are always going to be spectator ions. So I come back and I put together what I have: 2 silver, AQ plus dichromate, AQ yields my silver, 07 solid. This is a minus 2. So once again, I am balanced with regard to my elements and also my charge. I have a plus 2 here. I have a minus 2 with that compound. So overall, that cancels out. It's neutral. And then on my product side, it's also neutral. So I've met all of the things that I need to meet for it to be a good balanced equation. All right, so on number 3, I'm going to get y'all to try that. We'll talk about it a little bit first. This is just a typical strong acid, strong base neutralization reaction. In fact, this is probably the typical one. So once again, the hydrogen and the hydroxide is going to come together to form water. And then what's left over, the sodium and the chloride come together to form the salt. And in this case, it actually is salt. Sodium chloride, table salt. So what's sodium going to be? AQ, S, G, L? But think of it not just if I have it, think of it not if I have it like to put on food, but like if I put it in water. What would it do? It would dissolve, right? So it's AQ. And sodium's group 1, and they're always AQ, but yeah, that one we've actually seen. Okay, so that's going to get you started, okay? So remember, anything that is aqueous, that's what you need to ionize. And you can actually jump down to, we already kind of did as the molecular equation. We don't need to put any coefficients, it's balance. So take that information and jump down to your ionic equation. So the only thing that's not going to be broken up is your water, H2O. It's a liquid, it's never broken up. Let's see what you can do. All right, so we're just going to start ionizing. So we have H plus, and this one has no coefficients except for the water, no subscript. So it's pretty easy. You're just going to have one of each ion. And like I said, I'm not putting AQ, but you'll notice on your practice it is there just to kind of, because I keep on running out of room. Na plus Cl minus, and then H2O liquid. All right. So what cancels out?
Sodium chloride.
Sodium and chloride. And you end up with just what makes up water. Oh, that's right. And for any kind of acid-base neutralization reaction, this is what you're going to end up with. For any, I'm sorry, let me say that again. For any strong acid-base neutralization reaction, you're always going to end up with that same net ionic. You may have some coefficients with something, but you're going to end up with H plus OH minus gives you H2O. Because if it's a strong acid and a strong base, they're going to ionize. They're going to be AQ. Yes, ma'am.
And NaCl have to be in front of H2O, or can H2O be first?
No, H2O could be first. Think of it just like 5 plus 2 is 7 and 2 plus 5 is 7. You can switch them. Either way, same thing on that other side. NaOH could have been first or HCl. All right, so why don't y'all try the next one? It's very similar to the one we just did. Is lithium, LiOH, lithium hydroxide, is that a strong acid? No, it's not a strong acid. Is it a strong base? Is lithium hydroxide a strong base? Yes, ma'am, it is. You're right. And what about H2SO4? Is it a strong acid? Was it our list of 7? Yes. So it's going to be very similar, okay? You're going to get water. And then what's left over, which in this case is your lithium and your sulfate, those come together as your salt. Now you'll have to look at your ion and write the correct formula for that lithium sulfate because it's not just on a one-to-one basis. All right. It's kind of, I'm getting away from me there. Oops. Never fails where you try to go faster. just gonna, so on this one, I'm just gonna write the net ionic, because I think we're getting ready to run out of time. Oh, well, we all know what our net ionic is the same, right? Yeah, because whatever you ended up doing, you should have been able to cancel out everything, and then you would have just ended up with your net ionic, but you happen to have coefficients of 2 instead in front of everything. All right, so tomorrow we're going to continue on with that, work up in pairs for a little bit, and quiz will be on Wednesday. All right.